I must say that it's very nice to see all our friends from abroad as well, from England and from Holland and Israel and from Turkey. Welcome you guys down here in Africa, where we are supposed to having winter, although it almost feels like summer. So without further ado, I'm handing over to Gerrit Visser, who will lead this session. Thank you very much.
This session is on meshing, but it's part of a large series on meshing. So in this section, we'll look at mostly what do I want to know about analysis, because that determines how you mesh. Okay, so let's start first with an overview of what we need for accurate finite element analysis results. I'm not just looking at modeling at the moment. Modeling will be part of this. In order to get good answers, we need meshing that's got the right element types, whether it's beam, shells, solids, and so on. Apologies, I'm looking at the wrong slide. Okay, so this is the overview that just explains what we look at. So we'll start with an overview of start with what we need for accurate results, then look at meshing, which is the topic of this. All the stuff you see in white is what we'll cover today. Everything in this funny orange color is stuff that's still coming in future sessions on the same topic. Okay, so we'll start with element types, beams, shells. We'll briefly talk about the rest, but we'll cover a bit more time specifically for beams and shells. So we'll later on look at solid elements, planar, plane stress, plane strain, axisymmetry, and so on. The order of elements, accuracy versus computational cost of different element types. The effect that distortion has on the accuracy of a model, some different meshing strategies to get a good quality mesh, to get it fine in the regions that's important and coarser possibly elsewhere, ways to get that efficiently. For that we look at shells and solids specifically, and then some tricks to improve the accuracy of beam models. We'll already start talking about some of this in this session as well. Okay, so in other words, we can look at beam-only models or combinations of beams and shell modeling. I was at a conference about 15 years ago where one of the presenters started with this comment, and I think it's pretty apt in this regard. Where I want to go depends on where I want to end up with. So if I rephrase that in FEA terms, if you ask me how should I model, well, that critically depends on what you want to know. So in finite element analysis, we actually have to start at the end. Once you know what you want to know, you can then work back towards what kind of elements can do what I need. How do I need to model it? Do I need to mesh very fine? And so on. Okay, so this is now where we start with for accurate results. Each of the following must be accurate because these kind of stack. So the geometry has to be accurate. My usual comment is a 10 millimeter plate is not 10 millimeters thick. There's a little bit of tolerances. If I look at actual stiffness, it's linear with the thickness. But if I look at bending, the stiffness is to the third power with thickness, while the stress is second order in terms of the thickness. So small changes can cause significant errors if you're not careful, depending on the load and the load direction and the load type. Then the discretization of this geometry, because this is what we're solving, we're not solving the geometry. So this is a mesh. We also need accurate material properties, accurate loads, boundary conditions, that's correct. Unfortunately, there's no such thing as accurate or inaccurate. It's either right or wrong or reasonable at least. To be honest, that's one of the major causes I see of wrong results in finite element analysis, but that's a topic for another day again. Okay, then initial material state is something we often ignore. If I look at something that's formed or forged, I already have a certain stress state, which if I change something in that structure, I drill a hole or something, I can already relieve the stresses, which means I'll get distortion. So that's something we often ignore. But in certain analysis types, we need to be really accurate. In those cases, we need to find out what that initial stress state is. The load history also plays a significant role, especially if there was plasticity involved in some of the load cases or load steps in between. It kind of relates to the initial material state, except it builds on that and then takes the model further. So there's additional plasticity or whatever in the model. We also need to include all the relevant physics. It doesn't make sense if temperature plays a significant role to not include it, for example. If it's nonlinear, well, you have to run nonlinear analysis, obviously. Contact, each of those effects, if you miss something, you can get the wrong answer or not as good an answer as you would have had. The last one, unfortunately, is interpretation of the results can also significantly influence what you get out of an analysis. So two people can look at the same results and come to different conclusions. Okay, but that's, again, a topic that we'll have to discuss at a different point. In this session, we look at discretization of the geometry, the mesh, in other words. Okay, so some of the questions that we have to ask to determine the mesh type is, first, what do we want to know? A couple of simple examples. If I ask, will it fail? That is not a good enough question because it's extremely imprecise. You have to be very, very clear in what you want to know. So you can, for example, rather ask something like, will plasticity occur under the specific conditions, such as these loads, these boundary conditions, these material properties, etc., etc., etc. Once you have that defined, you're already closer. It's still not perfect, because if I look at plasticity, how do you define plasticity? Do we use a von Mises equation? Some of the more complex ones, do we have a material that yields in a totally different way than von Mises? But at least at this point, we're already a lot closer to what we want to know. Another question is, which element types are valid for our geometry? So we may ask whether we can use beam shells as solids, possibly combinations of these. Can we use planar models? By that I mean plane stress, plane strain, generalized plane strain, the axisymmetry models, the Fourier axisymmetry, all of those. So that is determined by the geometry whether it's physically possible. It doesn't necessarily mean it's the right element choice yet. It simply says I can kind of use these but not those specific elements. The next one is, what results are we interested in? If I'm only interested in displacements, pretty much any element, as long as it's a valid element, will be able to give me decent answers. But if I look at stresses and stuff like plastic strain, every element type has limitations. Beam elements, for example, as we'll see, averages pretty much every stress that you see, which means a load is applied evenly distributed over the whole face, in such a way that the section cannot even change its shape, which in real life does not exist. It's not possible for that to happen. If I look at plastic strain, again, beam elements, some type of beam elements can actually do it, some in a very primitive way, some in a more advanced way, but there's a lot of things still missing. So the results that I want to end up with, back to this first question, what do we want to know, also plays a significant role on the element types that we may choose. Okay, so another question is, where are we interested in these results? As I say, a beam element can generate stresses, but a beam element cannot give you any stress concentration answers. It completely ignores stress concentrations because there's not enough information in the formulation to take it into consideration. Okay, then very open question is, how accurate do I need to be? I specifically gave there's really a wide range of answers. In some cases, within 30% may be good enough. Most of you will probably shudder at that. But if we're early on in a design, and I need to compare 2 or 3 different designs to know which direction should we go, it's much better to give a really quick answer that's within 30% for all of those and to help me guide which of the directions I should go in. In some cases, we need to be really accurate. So we may be 1% or 0.001%. If you're experienced in finite element analysis, you'll know 10% is not that hard to hit. depending on the model, there's some models that's actually harder to get to 10%. 1% is pretty easy to get if your load is well defined, your boundary conditions is well defined, your material property is well defined, and it's a single part. If you need to go to something stupid like 0.001%, that'll be extreme cases of a very simple part where you're testing some new material model or something. But otherwise, we don't typically try and reach these kinds of levels. So I'd say most models we're trying to reach somewhere in this range, I'd guess. It doesn't mean that the others is not valid. Now, the reason I mention this is, depending on what I want to know, I might use a different element that's a lot easier to set up, easier to run, and get to this answer really quickly. Okay, so if you look at beam elements, when we study engineering, that's probably the first element that pretty much all of us learn about. It's a very simple element that you can actually push pretty far in order to help you understand quite a lot about engineering in general, stresses, strains, and so on. So we use these beam elements to learn the basics of loads and reactions. Yes, I know if you do statics, we don't even look at elements themselves. But exactly what we learn in statics transfers directly once we start looking at beam elements. So the applied loads and the reaction forces should perfectly balance. One of the first things that we learn in engineering. We also learn about the basics of stress and strain. So axial stresses, the axial load divided by the area, shear stress, which is the shear stress divided by shear force divided by the cross-sectional area, and the bending moment, the moment times the height divided by cross-sectional inertia of the section. So the first one is constant over the whole section. The second one is again constant over the whole section, but in a different direction, a shear instead of a direct stress. But the last one varies linearly from, let's say, maximum to negative, that maximum at the other side of the beam section. Again, this is approximate, except in the center of beam sections. Once we get too close to the ends where it attaches to something, or where the load is applied, that is not completely true. We also learn about statically determinate and indeterminate structures. Determinate simply means I don't really need to know what the structure looks like. I just need to know where the loads are applied and how it's constrained, and I can tell you what all my reactions are. That indirectly or directly is not that useful. We need to actually determine both the loads, the reaction forces, and then the distribution of these forces and stresses, how it influences how the structure behaves. Okay, so if we look at beam elements, what results are available? Yes, we have displacements and rotations. And I specifically mention this because there's some elements, once we get to solid, which does not have rotations in general. Yes, I know there's special formulations that sometimes have rotations, but in some cases, even those are not really a rotation. It's an intermediate calculation value. We also have forces and moments, which are great for calculating shear force and bending moment diagrams. If you're especially in the civil industry, where we work a lot with beam type structures, in those cases, we're not really looking at stresses. We're looking at the shear force and bending moment values and comparing that to load values applied or allowed for that section. If I look at the stress and strain, everything is averaged. It says that load is very smoothly applied over that whole face. It's impossible to get the stress concentration. If you look at the beam, anywhere you apply a force, that location has an area associated to it, and that force will be applied evenly over that area. Okay, so what can we model with this? Anything that, well, all of us know more or less what a beam section looks like. Anything that's a long and slender beam type section. And by that I mean the aspect ratio somewhere around 10:1 is often considered a reasonable starting point. Anything less than that is kind of dangerous. It does not mean you cannot do something shorter than that, but you have to be careful. There's a couple of things that you really need to know if you go for shorter sections than this. So what can you not model? Now, before I even mention each of those, when you see a star there, it's not the complete truth. Okay, so we cannot model a detailed connection. We do not have the information how it's attached. It's physically not there in the beam model, so we cannot model the detailed connection between beams. Along the section of the beam, fine, there is perfect. If I look at very short beams, again, unless I take very specific precautions, it does not make sense to use beams. You'll get the wrong answer. If you have curved beams, your normal beam formulations will not work. So in other words, if I have some kind of a pipe with a radius going to another section, again, you cannot mesh that elbow section, the radius, using smaller beam segments and just apply straight properties to that, because you'll get the wrong answer. There are special beam element formulations that can do that correctly. I may be wrong, but if I remember correctly, the reason for that wrong answer mostly has to do with how shear loads and torsion loads are applied in a curved section versus this approximation of a lot of shorter straight sections. And again, we cannot get accurate stress and strain. Yes, in the center of the beam sections, we can get reasonably accurate results. Just one comment. If I look at the previous slide, we had that example of the shear stress being the force over the area, the shear force over the cross-sectional area. That does not exist in real life. It's impossible to get to that stress state. And the reason for that, if you remember correctly, would be the stress, the shear stress on the top of the beam has to be zero and the bottom, because of the way that the stress tensor works. So that means we end up with that hopefully familiar parabolic stress distribution shape through the thickness. So the peak value there is in the center of the beam section, and it's higher than that average that we've calculated before. It doesn't mean that average is not useful, but it's not, if I try and measure, I'm not going to get that shear stress that I'm predicting there. So why is the slenderness important? So let's look at a very short beam, which is actually outside of the theory for beams. Okay, so if I have a section like this height is about 20 millimeters. Let's see, I think it's no. So that height is 20 millimeters. That is about 100 millimeters total. The aspect ratio of this I've worked out was around about 2, maybe a bit less. At first glance, when you look at this kind of a structure, and even if it's part of a larger structure, it looks like a beam. We want to model it like a beam. Okay, now if I model this using curves to show where the centers of the beam section will be, that section there at the back with that thing stopping there represents this beam and that beam. Now what do we do between those two? And that's exactly one of the major reasons of why we have to be careful when we model with short beams. Because what I do there critically changes how the structure will behave. So in this example, I just extended the curve all the way to the end, and then I mesh these and apply the beam properties. Okay, so this is what it would look like. I've just plotted the beams expanded. Now, notice one thing though. These little lines that you see there represent all of the beam elements. So my beam elements in the length direction is actually way smaller than I need. But also it sounds worrying, because if I look at that section, that beam element is much shorter than that section and that section length. To give you an idea, the beam element was 2 millimeters long, but that height is 20 millimeters. Is that an issue? Is that an aspect ratio issue? No, it's not. The aspect ratio refers to the beam as a whole, not locally what the element looks like. I've seen lots of examples where people try and argue that it's about the element size. It has, for shells, the equivalent would be when the element itself is smaller than the thickness, it doesn't make sense, and that's not true. If you need to mesh that fine and the answers still keep on changing, then you're not inside shell theory. But if you mesh finer and finer, the answer will converge. It will stop at some point, but usually the solver will tell you that there is an issue. But that's due to round-off errors that starts causing problems. before that starts, the solver will already stop and not run the analysis. I did a test a long time ago, and it was something like one beam element section. If you model that with 100,000 elements or something insane, that's more or less when I started running into that kind of an issue. Okay, so I ran the analysis. What I did was I constrained it at the top for all of those, and I applied a shear load on all of those, the same value. And there you can see the deformed shape. But if you look at the color, you'll already vaguely see it's not exactly the same deformation. This is a kind of orange, a bit more red and a bit more yellow, meaning that one deforms the most, this one the least, and this one somewhere in between. Okay, now I'm going to step back to this slide in a moment because there's something really important that I want to show you. But first, let's see what happens. If I look at the tape measure, and let's assume the answer is correct. We may actually need to measure a bit finer to get a slightly better answer, but this is a pretty decent answer. In this model, for the loads that I've applied, the size of the structure, I get 3.07 millimeters displacement for this model maximum. It's that vertical displacement. If I rigidly connect that point to that, because that material doesn't exist, I get 2.33, or if I extend the beams, I get 3.32, which at first glance sounds like this is the nicest one to use if I use beam elements. Now let's just go back a little bit and see why would this one deform. Well, no, let's first try this one. Why would this one deform more than this one does? Because I've got a rigid connection there from there to there, which is kind of supposedly that attachment, and that's exactly the issue. If I look at the form shape at the back, I'll see the slight S, but if I look at the front, I see a significantly more exaggerated deformed S shape at the front. And this is exactly the reason why slenderness is an issue with beam elements, because this joint stiffness, the attachment stiffness, plays a critical role in what the final displacement there will be. Imagine this beam is infinitely rigid, but it rotates a little bit there, then that point will move down already. Good. If I change it, let's add some stiffness. Again, it's not the best way, and this is typically not how it's done. I just want to show the effect of this. I add some stiffness there to try and stiffen up the section at the back, so that beam section for this model behaves a bit more like a beam. So the shape at the front and the back is now closer to the same. Already I can see a difference in the answer between these two. Okay, now how would I model this with a beam section? Well, one would be I extend that to the center. What do I do with that little bit at the back? So unfortunately it doesn't show there at the back. You can see that little bit of penetration, but there's stuff kind of missing at the back. I'll probably model this very similar to the way you'd model that one where that I-beam is welded on but without stiffness. But in reality, it's a significantly different model. If I look at the answers for the solid model, I already see a significant difference in the displacement for these two sections. If I now assume this is the correct model, I get this for a displacement answer. So total displacement is now 2.71. The TET10 solids, but without the stiffness, is 11% more. The one with the rigid connection is 14% less, but the beams that's extended is now 23% more, which is significantly more than the previous model had. Even though it's exactly the same, those two, nothing changed. It's just the stiffness in the real structure that changed. If I use a slender beam, and this is just over 10, I think it's about 12 aspect ratio if I look at that length compared to the height of the beam section. And again, if I model it with beams, there you can see that overlap. I get the displacement type for the three, and then I compare the results, and now they're already so significantly closer together with a maximum error now with the rigid connection being 10% difference instead of 6%. So now we do the same. We add that stiffener and see the new effect. So it goes from 3.57 to 3.46. So that's a much smaller change than before. It's now only a 3% difference between the two solid models, but now -7.5 and -3% for these beam models. So if I compare this, and I go back to this slide, just by increasing the length, doesn't matter which one of my models I have, I'm significantly more accurate by simply increasing the length of the beam. So why would that be? Simply because the effect of that local rotation becomes less and less the longer this beam becomes, because this thing, as it bends, if you look at where far below it would be, there it moves just a little bit below, but there it's a lot lower. So is that quadratic or third power or whatever effect in terms of displacement? And I say different orders simply because it depends on the kind of load that you apply. Whether it's a constant shear load or a tip load or whatever will change exactly what the order of that parabolic order of that shape will be. Okay, so if you compare the results, I've just, for the short beam, copied the two sections so that the center, that TED10 is the first model, that one is the additional, the stiffened one, and there you can compare the results. So the rigid connection goes from under-predicting by 32% to under-predicting by 14%, while the beams were extended all the way, went from 8 to plus 23. So this one over-predicted the displacement. There it over-predicts it severely. Okay, now why did it over-predict it? If I go back again, that material for the beam that I added there has got stiffness. So as I apply that load, that beam already bends. So effectively, I'm adding in series a stiffness. If you add spring stiffness in series, you're reducing the total stiffness. If I look at the rigid one, you'll see it actually improves. It goes from severely over-predicting, under-predicting the displacement to less under-predicting, simply because in this model, the stiffness significantly improves the behavior for that connection, meaning it behaves more like a beam at the joint itself. If I look at the long beam, though, again, you can see it's now significantly less of an error based on the different models. Okay. If I look at shells, we have very similar behavior in terms of aspect ratio. In this case, aspect ratio is the shortest dimension of the plate normal to the thickness. So let's say a 50 millimeter by 10 millimeter by 1 millimeter plate. The shortest would be 10 millimeter divided by 1 millimeter. So we're just about there. I say just about because it depends on whether you use thin shell or thick shell, which we can talk about later. It depends on how accurate you need or want to be as well. So if you really want to be accurate, you'll have to push this to 20 to 1, possibly even 50 to 1. Okay, shell does not model through thickness stresses. Yes, there's strain through the thickness, but there's not stress through the thickness. So if you apply pressure to the one side, due to bending and so on, you'll see a stress, but definitely not due to the pressure directly applied to that structure. It also means we cannot model through thickness stress concentrations. So if you have different shells that you attach to each other at sharp corners and so on, yes, you'll see an effect, but through the thickness effects, think, for example, something like necking. As you stretch it, it starts thinning down. That cannot be taken into consideration. If the necking is through the thickness at least. Okay, then what can we model with it? There's a couple of beam-like structures that we can use. So all of these previous examples that I've shown you, I could have just as well have done with shell elements. We can get more detailed results than we'd get out of a beam model. We get joint stiffnesses because we're actually modeling the joint itself, which is really, really important to get the total behavior. We can see stuff like flanges that deform. If I apply a load to a flange, that flange will bend away, while in a beam model, there is no flange to apply the load to. It'll simply apply that load evenly distributed over the whole section. The one important bit, though, is it's significantly more expensive to run than a beam model. And the reason for that is multifold. Under perfect bending and strain conditions, which is pretty much what we have in the center of a beam section, the beam is an exact representation of reality. For shells, we have all of these aspect ratio issues per element as well, so we can't model something that's 10 to 1 aspect ratio and expect a good answer, which forces us usually to model using significantly smaller elements than we'd need using beam elements. So firstly, we reduce the element size, and in addition to that, since it's square or area kind of a shapes, the number of elements increase with the square of that reduction in element size. So in other words, if I measure surface with 10 elements and I halve the element size, I end up with 40 elements. So 4 times, because it's double the number of elements in each direction. So that makes it significantly more expensive to run a beam model, a shell model than a beam. Interestingly enough, shell models are usually easier to set up, not always, but usually. Beam elements with that beam orientation and so on that you have to check in the beam sections can actually be a bit more of a pain to set up physically. But to run it itself is a lot faster. Another very important thing about shells is the element choice is really important. Okay, so this is an example I typically use to explain the limits of accuracy. By that I mean the best possible behavior I can get out of an element. I'm looking only at the membrane. Yes, in bending it behaves. The element, a normal shell element can bend and has bending stiffness, but even then it effectively uses membrane methods on multiple layers. So we're first looking at this in the plane only. So if I look at a first order tri element, it's got 3 nodes, a first order quad has 4. If I look at the number of degrees of freedom per node, I have 3 and 3, translation X, Y, and Z. The reason for that is it's a membrane element. I'm not looking at rotations. So the total number of degrees of freedom per element would be the product of these two and product of those two. So it's 9 and 12. The number of rigid body modes that you have to be able to represent for this element is 6 in both cases. The element has to be able to translate in X, translate in Y, translate in Z, rotate about X, rotate about Y, rotate about Z without generating a stress. If the size and shape of the element does not change and you get a stress, then something is seriously wrong with that element. So that's why we have to be able per element to represent all 6 rigid body modes, meaning if I translate or rotate it without changing size or shape, the stress should stay constant. So with the number of degrees of freedom per element, that's the number of variables we have to calculate displacement and strain. And by displacement I mean this, and then the strain is the part of the displacement that's changing the shape. So from these 9 variables, 6 of them goes towards representing the rigid body motion, stress-free motion in other words, and only 3 is left to stress and strain with. If I look at the quad element, 9, 12, that doesn't look like a big jump, but once I subtract that 6, it goes from 3 variables to calculate strain to 6. If I look at the stresses I can calculate, or the strains for that matter, the same. I can calculate a constant stress in the X, a constant stress in the Y, and a constant shear strain. But once I've done this, I don't have any additional info to calculate any gradients. So this is what they refer to when they talk about the constant strain element. That means that element has a constant stress in every direction. X and Y can be different, but the stress anywhere in the X direction on that element is the same as any other location in the X direction. If I look at this, the quad element, I get 2 additional terms that's really useful. I can get a change of the stress in the X direction as I go in the Y direction. I'll show that in a bit. And I also have a change of stress in the Y direction as I move in the X direction. In other words, I've got 2 gradients. The last term is not a very useful one, unfortunately. So it is possible probably to use it, But this is if you warp it. Think if you have a square section and you move the diagonal points down and the other two diagonal points up, that weird deformed shape, what is the stress state for that? And the answer is there is no real sensible answer, which means that that additional degree of freedom is not that useful to calculate additional stresses. So if I move this, let's say I want to see what constant stress look like. This is what my load will be if I have a single element. If I apply that forces to these two tries or that single quad, I'll get exactly the right constant stress in the x direction for both elements. I can do the same for y, it's just no different direction. And these forces or stresses that will end up will be different to that x. So in other words, x and y is independent of each other. And again, I get a perfect answer. Shear, okay, I know you're probably not too familiar with this definition of shear. Think of it this way. If I apply a shear load in this direction to the right and at the bottom to the left, then if you look at that very small local part of material, there's also a force in that direction which matches this one, and one down that matches this. So this is simply a different way of looking at shear stress. So this will generate a perfect shear stress in theory, at least for that element. For both of those, we can get exactly the correct shear stress. The element formulation allows it, the number of variables that we have to calculate it, so again we can do all of those. Now for the bad part, if I look at some kind of a gradient, so if I apply a bending load to this section, I've got a high stress there and goes through zero and then reaches a compressive stress at that location. In this case, there is no d sigma x dy term for a tri-3, which means I cannot represent a linear variation through the thickness with that, while I can represent it with this. Now, I have to step back a bit and say, remember when I said this is the theoretical limit of accuracy? Due to the element formulation, this is not always perfect because there are certain complications that arises. But the best possible that it can get to is it can represent the stress state exactly if you have a perfect element formulation. What will happen though if I apply this load to this element? Well, this one will move to the right, this will move to the left, out, in, so similar to bending, where again the left, in, out, in. But if you look at the stress state, this element will be in tension and this one will be in compression, but that element will be in tension over the whole element, and this one will be in compression over the whole element. And whatever that tension value is will be more or less the same as what this compression value is. And I then average that tensile and compressive. It will say there's a zero stress. There is some stress, but it's not very high because it's this average tensile value. Again, zero because it's averaging a tensile and a compressive value that's about the same. And I'll get a compressive value at that location. So I'll get a pretty weird stress distribution. For this element, after applying that load, I'll see that linear stress distribution through the thickness. So it's going to be pretty close to what it's supposed to be. Again, if the element was perfect, it can actually get exactly that stress state. Just the same, there's now for a d sigma, sorry, see there's a mistake, it should be d sigma y dx. In other words, the stress in the y direction vary in that direction. And again, the quad can represent it, the tri-element cannot represent it. So the problem with this is for tri-elements, this model and this one has exactly the same number of nodes. It's got more elements, but it's a less complex element. So in terms of setting up the stiffness matrix and at the end back substituting, this will probably be slightly faster. In terms of matrix solution, they'll be exactly the same because they've got the same number of degrees of freedom. But if I want to model this bending, I'll get a horrible answer out of this and I'll get a really good answer out of this. If I start refining this mesh to have 3 or 4 through the thickness, I'll start getting an okay answer. But 3 through the thickness would mean 4 nodes by 4 nodes. So that's 16 instead of 4 nodes. And my answer will still be worse than whatever the quad 4 would be. again because I've got these constant values. Once we extend this to 3 dimensions, the equivalent would be a x8 on this side and a TET4 on this side. So what I typically tell new users in any of the courses I present is the purpose of a try-3, and by that I mean a try-3 mesh only, not 1 or 2 try-3s in a mesh. So the purpose of a try-3 or a TET4 is either to lose your job, if you're lucky, or to kill somebody with, because it's severely inaccurate. Okay, now if you're a more advanced user, there's a lot more nuances to that, because you know at some point you need to mesh significantly finer, and what a good mesh looks like for a TET4 is different than it would be for a TET10 or a X8 or whatever kind of a model. But they're extremely dangerous if you're not careful about using them. Okay, but that more or less brings me to the end of this section. Just in summary, we talked about what we need for accurate results, and for meshing, we started with the different element types, beam shells. We'll still look at solid, and we'll talk a bit about the planar elements, axisymmetry elements, and so on later on, together with effects like the order of elements, the accuracy and computational cost of different elements, how they compare, the effect that distortion have, and how to then effectively minimize distortion in a mesh, and then some specific meshing strategies for shells, solids, and then at some point also more accurate beam modeling.
If there are any questions, you're more than welcome to ask them now. There was one question in the chat, and the question was, what is your reference to make a statement on the accuracy?
Okay, I'm not saying what the question is because it can refer to so many different things. If it was about that difference between the TET4s and the TET10 mesh and the beam elements, I'm not saying that the TET mesh there is correct, but it's closer to reality. If it's a more general question about accuracy in real life, if you can just explain what the question is, I'll try and answer that a bit better.
Simon, if you're still here, can you maybe just elaborate on the question that you had? You're welcome to unmute your microphone. So maybe Simon is shy. If there are any other questions, you're welcome to type it in or unmute yourself and ask the question. Otherwise, thank you for attending today's seminar, and please leave us your feedback and don't forget to register for the next session. Gerrit Zak just made a comment. He said, do you think Simon referred to the 30% to 0.001% accuracy figures that Gerrit mentioned?
That was just random numbers. Most people will probably try and aim for somewhere between 1 and 10% at a guess, because in a lot of cases we're not working with early models. We need to qualify certain results for a model, qualify the structure effectively. So in those cases we need to be reasonably accurate. It doesn't need to be perfect, because that's part of the effect there would be to take safety factor into consideration. But there are cases where we, for whatever weird reason, are either allowed to use much looser tolerances or, on the other side, much tighter. I think it will be actually really hard to get to that 0.001% accuracy, but it is possible for very simple structures. Imagine a plate with a hole in it, you're clamping it, and you want to see what the strain state is on that inside edge of the hole. Fine, it's possible. You just need to measure it fine. But the question is, why do you need to go so far? And the answer is, I can't think of any.
Thanks, Gerrit. And then a remark from Christy. It would be interesting to see the effect on eigenvalues as well for those examples.
The eigenvalue stuff is actually surprisingly easy to estimate what the effect would be. If I look at those first models, mass of the one structure, the actual solid, and the mass of the first model that I had with beams that I had the rigid in will be identical because it's got exactly the same outline shape. If I then compare the displacement, that's directly related to stiffness. So if I take the square root of that difference, I'll get an indication of what the change in natural frequency will be for that model. If we extend that to the model where we extend those elements to the end, in that case there will be a little bit additional mass. So that will change that same approximation that I've used slightly, but because of the location where it is, that mass does not play a very large role. The mass at the end of the beam where it moves the most is the most important in that kind of a model. So in this specific case, I don't expect a much larger difference in eigenvalue than the square root of the difference in the displacement. So the advantage of an eigenvalue method, or a modal method rather, is the frequency is actually pretty easy to get right. If I take, for example, a 10% error, so it's, let's say, times 1.1 in terms of the displacement, square root of that will be around about 1.03 off the top of my head now. So that means a 10% error in stiffness would translate into about a 3% error in natural frequency, assuming the mass is correct.
I think that's sufficient. Thank you so much, Gerrit. It seems like there's no more questions. Thank you, everybody. Have a good weekend.
Thanks. Bye, everyone.